Let's say you have a tire and you're trying to compare 2 points on this tire. The first point is out here near the edge of the tire, and the second point is closer to the center of the tire. So we're going to take a look at the velocity of these 2 points. And let's say that after some time, the tire rotates so that it's on its side. And so the new points will be here for this outer point that we had before, and this inner point will be translated to over here. So it looks like it shifted about 90 degrees. So the velocity for this point is going to be the distance it traveled, which is going to be the length of this arc, over time. And that's basically just the definition of velocity. Now the velocity of this point is going to be this distance over the same amount of time. The problem here is that the velocity of this point is much greater than the velocity of this point, because this point traveled a greater distance than the inner point did. Well, what if we had a variable that was the same for both of these points, regardless of how far they were away from the center of the tire? And that's where rotational motion variables come in handy. What we're looking at right now is angular velocity, which is written as the Greek letter omega. So angular velocity for these 2 points is going to be the same because angular velocity basically measures the angle that a point has rotated or traveled in a particular amount of time. So from this position to this position, the angle between these 2 points is going to be about 90 degrees, and the angle between these 2 points is also going to be 90 degrees. So any points that are on this vertical line will have the same angular velocity as the tire rotates around 360 degrees. And so the angular displacement is going to also be the same, because the angle that they rotated, or the amount that they rotated, is also going to be the same quantity. And the way that we're going to write this is delta theta. Notice how angular displacement is kind of written like translational or linear displacement, which is delta x. Both of them have a delta sign in them, which means change in. So for angular displacement, we're talking about the change in the angle, while for linear displacement, we're talking about the change in the x position. So also, angular displacement is going to be measured in radians. So you know how angles can be measured in degrees? Well, angles can also be measured in radians. And if you didn't know, the conversion factor for degrees to radians is going to be 180 degrees over pi radians. So, or you can flip this over to be pi over 180. But if you had, let's say, a 30-degree angle and you wanted to convert that to radians, just multiply by the conversion factor, and the degrees cancel out, giving you radians on top. Now moving on, for our angular velocity, that's going to be measured in radians over seconds. And I'll be rewriting this later on in the video, so just bear with me and my messy handwriting. But the angular velocity is basically going to be the angular displacement over time. And so our units make sense for that because angular displacement is measured in radians and time is measured in seconds, so it's radians per second. Now angular acceleration is going to be, you guessed it, velocity over time. Doesn't this look a lot like translational acceleration, which is velocity over time? Well, it's not really a coincidence, and we'll be going over these similarities in the next video. But anyways, angular acceleration is going to be written with an alpha symbol, and that's going to be measured in radians per second squared. Now the next variable we'll be looking at is the period, and that's going to be measured in, or that's going to be written as a capital T, and that's going to be measured in seconds. Now what the period is really going to tell us is how long it takes for one point on this object, or this tire, to rotate around a full 360 degrees. Now the torque is going to be written as the Greek letter tau, and we did go over this in a previous video, but what torque basically is pretty much a tilting force. So any disturbance that causes an object to shift a little or rotate in a particular way. So torque is going to be measured in newtons times meters, because as we also said in a previous video, torque is equal to force times the cosine of an angle between the force and the object times distance. So this quantity is going to give us newtons, and this quantity is going to be in meters, so that's going to be newtons times meters. Then the next thing we're going to go over is the moment of inertia, which is written as a capital I. And if you remember this word inertia from when we were going over Newton's laws, inertia is basically an object's resistance to move. And so the more inertia you have, the less likely you're going to be moved when something disturbs you or a force pushes against you. Similarly, the moment of inertia for a rotating object is going to be a measure of how resistant it is to changes in its angular velocity. Now this is going to play a part in angular momentum, since angular momentum is equal to the moment of inertia times the angular velocity of an object, and this is going to be written with a capital L. So angular momentum is similar to translational momentum, which remember is written as P. So angular momentum is basically going to be an object's moment of inertia times the velocity that it's currently rotating at. And this will be measured in kilograms times meters squared. Now, if these last two seemed a little confusing to you, don't worry, because I'm going to explain them in further depth in a different video. But for now, I'm just going to create a table with all of the rotational motion variables, their symbols, and their units, just so that you can actually read all of this. So here's a handy table that I made with all of the rotational motion variables, symbols, and their corresponding units. If you want, you can pause here and copy down this table, and I hope it helps.